Study Unit 1, Lecture 4. So the previous lectures discussed the basic principles behind the operation of a diode, but the homogeneous p-n junction can actually be modified to get different types of diode and change the way that the p-n junction behaves. The most obvious way in which the p-n junction can be altered is by varying the doping densities on the p and the n side. So in this example here, the p side has a very high doping density, while the n side has quite a low doping density. By varying the doping density, especially on the n side, which is normally where the doping density gets varied, the resistivity and reverse breakdown voltage of the diode can be altered. In this example here, the space charge layer has penetrated much further into the n region than it has into the p region over here. The primary disadvantage of using such low doping densities in the n region is that the resistivity increases even though the reverse bias voltage is now much higher. So what happens is that there is a larger voltage drop over the p-n junction as current flows through. A good way to circumvent this problem is to make the p-n junction much wider than would normally be required. So what would happen is the diode would have a very wide p-n junction over here. Another advantage of using very wide junctions is that the thermal performance of the diode is also improved. One of the ways in which the thermal and current problems of p-n junctions with lightly doped n areas are compensated for are by having asymmetrical doping profiles and asymmetrical silicon structures. So in this example here, the p region is quite narrow in comparison to the n region over here. The problem with this is that at the edges of the junction over here, there are breakdown problems which need to be compensated for. Ways in which these edges can be protected is by making use of guard rings or by beveling the silicon region in order to avoid high breakdown voltages appearing at the edges. The speed at which the diode switches is determined by the lifetime carrier of carriers through the space charge layer. In other words, the longer the lifetime of an electron or carrier through this region over here, the longer it will take the diode to switch, because once the polarity around the diode has changed, the lifetime of that carrier must first be expended before a charge will stop flowing. One way of improving, or rather decreasing, the carrier lifetime is to introduce gold or platinum into this neutral region, so that these atoms provide absorption centers for the carriers, thus reducing carrier lifetime. One of the problems with making diodes out of thicker and thicker wafers of silicon is that the transient properties of the diode start to degrade. In other words, the thicker the junction area, the worse the ability of the diode is to switch from one state to another. The problem of very thick wafers is overcome by using a new diode structure. These structures are called PIN diodes, where the I stands for an intrinsic doping profile which exists between the p and n regions of the diode, in a way to customize the intrinsic region in the diode over here. The doping profile in this region can be customized to have a certain electrical field distribution. So in this example here, there's a very sharp fall off across the doping region, whereas in this example over here, the electrical field strength falls off more gradually between the n and p regions. This intrinsic region is normally modeled as a low concentration n-type region, which is sandwiched between the p and n regions. The low doping concentration of this intrinsic layer allows the space charge layer to extend across the layer between the p and highly doped n regions. Once again, by being able to control the density of the doping in this region, the doping profile, the electric field strength can be controlled, and this allows for a more compact device as opposed to very thick wafers with only a single junction. The symbol for PIN or PIN diode is no different to that of a normal diode, and a designer will have to look at the data sheet to determine what type of diode they're using. The next diode under consideration is a special type of diode called a xenodiode. A xenodiode is a type of diode where the reverse breakdown voltage is designed to be purposefully low. In other words, the reverse bias which is required in order to get breakdown to occur across the xena needs to be quite low before current will flow. Once the reverse bias across the Zener has exceeded the designed amount, which is normally a few volts, then the main breakdown mechanism is avalanche multiplication rather than Zener breakdown, after which the device is named. Zener diodes are useful in low power electronics as clamping devices which will clamp a voltage across the terminals to some value which is designed into the device. In general, they are avoided in power electronics. Finally, the reverse Zener voltage is determined by design, and the symbol for the Zener diode is very similar to the normal diode with a slight modification to the crossbar around the triangle. The next diode which will be considered is the Schottky barrier diode. The primary characteristic of the Schottky barrier diode is that the forward voltage across the diode, which is required in order for there to be a conduction path, is very, very low. Typically, the amount of forward bias required to conduct through the Schottky barrier diode is a few hundred millivolts, as opposed to nearly a volt or 2 volts for a typical diode. A Schottky diode has a similar structure to a normal diode with one key difference. This difference is that there is no p-doped region in the Schottky barrier diode. Instead, a barrier metal is used in contact with a layer of n-type silicon, which is then in contact with a heavily doped N+ substrate. When the device is forward biased, only electron carriers will flow from the cathode through the heavily doped region, through the N-type silicon layer, and then to the barrier junction, which is between the N-type region and the barrier metal. Because there are only electron carriers and no p region to provide positive carriers, the Schottky barrier diode is a unipolar diode. In other words, current can only flow from the cathode to the anode. There are some key distinctions between the Schottky barrier diode and a normal p-n junction diode. In a normal p-n diode, there will be some reverse bias current which is caused by minority carriers drifting across the space charge region. So for example over here, there will be some reverse bias current which flows from the N region to the P region. This is not the case for the Schottky barrier diode. In the Schottky barrier diode case, the reverse bias current is caused by majority carriers which overcome the barrier potential which exists at the interface between the metal and the silicon. An advantage of the Schottky barrier diode is that the electron carriers are swept across the region and then combine in a metal layer. This means that the Schottky barrier diode is able to switch incredibly quickly. Under forward bias, carrier injection only comes from the N region, and there is little recombination in the space charge layer. So for this reason, the Schottky barrier diode can be approximated by the ideal diode equation. In fact, where other diodes will have a curve similar to the Zener diode IV characteristic, the Schottky barrier diode will have a very linear relationship between the current and the voltage through the device. Finally, the majority carriers all come from the N region and have a much higher energy than a typical diode, and for this reason the Schottky barrier diode is sometimes referred to as a hot electron diode.